So, have you ever stopped to think about something like how you can take two vectors, say the force you put on a wrench and the lever arm of that wrench, and somehow multiply them to get a third vector, the torque that actually turns the bolt? I mean, it's not like regular multiplication, right? This needs a totally different kind of operation. All right, let's really get into it. Today, we're going to break down the vector cross product. It's a super important tool in physics, in engineering, you name it. We're going to look at what it is, how you actually use it, and, why it matters so much. So here's the plan. We'll kick things off with the basic definition, then get into how to figure out its direction and its size. After we've covered the main properties, we'll see where it pops up in the real world, and then we'll actually solve a problem together. Let's get to it. Okay, first things first, what in the world is a vector product? Well, you're probably familiar with the dot product, which takes two vectors and gives you a scalar. Just a number, right? Magnitude, but no direction. The vector product is completely different because the result is a whole new vector, one that has both a magnitude and a direction. And honestly, the definition is pretty much right there in the name. When you multiply two vectors and what you get out is another vector quantity, you've just done a vector product. We also call it the cross product, and you'll see why in a second. And here it is, the mathematical heart of the whole thing. This formula, A cross B, it really has two parts. The first bit, AB sine theta, that tells us the length, the magnitude of our new vector. And the second part, that little n hat symbol, that's what we call a unit vector. Its only job is to point us in the right direction. We're going to unpack both of these pieces right now. So about that direction, how do we actually find where n hat is pointing? Well, for that, there's a really simple but kind of cool physical trick we can use. It's called the right-hand rule. You can literally do this with me right now. Picture two vectors, A and B, starting from the exact same point. Okay, take your right hand, point your fingers in the direction of the first vector, A. Now curl them towards the second vector, B, making sure to go through the smaller angle between them. See where your thumb is pointing? That's it. That's the direction of your new vector, A cross B. And what's really important is that this new vector is always perpendicular to the plane that A and B are sitting in. So we've got the direction down, but what about the magnitude? That AB sine theta part? It's not just some random calculation. It actually has this really elegant geometric meaning behind it. And this is the key takeaway here. The magnitude of the cross product gives you the exact area of the parallelogram you would get if you used vectors A and B as its two adjacent sides. Think about it. The more perpendicular those vectors are, the bigger the area, and so the bigger the magnitude of their cross product. It's a perfect visual representation. Now, just like any other operation in math, the cross product has its own set of rules, and knowing these is going to be absolutely essential for using it correctly. I think this slide is so useful because it shows the two extremes. When your vectors are perpendicular, the angle is 90 degrees, and the sine of 90 is 1. Bam! You get the maximum possible magnitude. But if they're parallel, the angle is 0, and the sine of 0 is 0. So the whole cross product just becomes a null vector. It has 0 magnitude and no real direction. And that makes total sense geometrically, right? You can't make a parallelogram with two parallel lines. And here are three more really critical rules. First, order matters. A lot. It's non-commutative. A cross B is not the same as B cross A. In fact, it points in the exact opposite direction. Try it with a right-hand rule, you'll see. Second, if you cross a vector with itself, you always get 0. That just follows from that parallel vectors rule we just talked about. And finally, it does play nicely with addition. It's distributive. Okay, so we've got the concepts down. But in the real world, you're usually going to get vectors broken down into their x, y, and z components. So how do you calculate the cross product then? Well, luckily, we have a very systematic tool for that, and it involves using something called the determinant of a matrix. This is the standard setup you'll see everywhere. You build a 3x3 matrix. The top row is always your unit vectors, I hat, j hat, and k hat. The next two rows are just the components of your vectors, a and b. You then just calculate the determinant of this matrix, and what you get are the components of your final resultant vector. It's a really neat system. All right, so this math is pretty powerful, but what's the point? Where does this stuff actually show up? Let's bring it back to the world of physics. And here we go. This really brings it all home. Torque, the very concept we started with, is literally defined as the cross product of the position vector r and the force vector F. It's the same story with the magnetic force on a moving charge. It's found by taking the cross product of its velocity v and the magnetic field B. And notice, in both cases, the resulting force is perpendicular to the original vectors. That's a direct consequence of how the cross product works. Okay, time to put all this knowledge to the test. Let's walk through a pretty common type of problem, one that actually connects the cross product and the dot product. So here's the puzzle. We're told that there's a relationship between the size of the cross product and the size of the dot product. Our job is to use that clue to figure out the angle theta between those two original vectors. Let's just take this one step at a time. First, we just write down the information we were given, but as an equation. Easy enough. Next, we swap in the formulas we know for the cross product's magnitude and for the dot product. Now, look at that. The a/b terms are on both sides, so they just cancel out. That leaves us with sine theta equals √3 times cosine theta. If we just divide both sides by cosine, we get tangent theta equals the square root of 3. From there, you just solve for theta and you get your answer, 60 degrees.
And let's end with something to really think about. You know, the right-hand rule, it's just a convention. It's something we all sort of agreed to use. But what if, way back when, we had picked a left-hand rule instead? Well, our vectors for torque and magnetic force would point in the complete opposite direction. The physics of what's happening wouldn't change, of course, but our mathematical description of it would be a mirror image of what it is today. It's just a great little reminder of how we build these models to understand the world.